Hello, and welcome to Lecture 2. In this lecture, we're going to start Chapter 2 of Survey 10th edition, and we're going to cover the topics of position, displacement, and velocity in a single dimension. Our objectives are to distinguish between distance and displacement, apply the relationship between a particle's average velocity, displacement, and time interval, distinguish between speed and velocity, interpret position versus time graphs, recognize the instantaneous velocity of a particle as the tangent of a position versus time curve. All right. So let's get some key terms out of the way. So first of all, a term we're going to see quite a bit and is not unique to these sections nor this chapter is the idea of a particle, which is a very small thing or a simplification of a larger thing that we just don't care about the details of. Okay? An object that can only translate is a particle. It can only move in the x, y, and z directions. That is the only type of motion it can undergo. What does this mean? In other words, it cannot rotate. Okay? So it's an object that cannot rotate. All right? So, moving on, we have kinematics. Kinematics is the study of motion. Broadly, that's what it is. Okay? It refers to displacement, velocity, and acceleration. So in practical terms, if someone is talking about kinematics, then what they're talking about is displacement, velocity, and acceleration. In a sort of poetic sense, it is the geometry of motion, since it doesn't care about the cause. It does not consider the cause of motion, in other words, forces. Kinematics is a study that only concerns itself with the result of motion. It is the how, not the why, of motion. Okay, so we have a few fairly simple formulas for this introductory chapter. And let's get those formulas and the terms in those formulas out of the way. So first of all, we have displacement. Displacement is just delta x. It is the final position minus the initial position. Here the subscripts are 2 and 1. Those are not the only subscripts you're going to see for final and initial. You might see x final minus x initial. You might see x minus x naught. It is important to get used to different notations that are conveying the same idea. V average is, well, AVG is a subscript, means average velocity. So V for velocity and AVG for average. It can also be represented as V with a bar over it, and is defined as the change in displacement, as the displacement over the elapsed time. So the delta x over the delta t. Delta is a Greek letter that denotes change, okay? And this is the uppercase delta if you're typing it out. So in other words, it's just x2 minus x1 in the numerator and t2 minus t1 in the denominator, okay? So that means that the units of average velocity must be meters per second. Okay? So that's average velocity. We'll see a lot of velocities in problems throughout this semester. We also have average speed, same subscript. Now the difference between speed and velocity in terms of their formulas is that the numerator for speed is total distance, not displacement. Total distance is the sum of the absolute value of individual displacements. So it would be the sum of the absolute value of individual displacements for I to infinity. Okay? Let me show that to you one more time. The sum of individual displacements like that. Okay? See? So I'm just summing up the absolute value of individual displacements. The subscript I just notes that there could be any number of them, and I'm just summing up each one. Okay? The last formula is for instantaneous velocity as opposed to average velocity. The difference between instantaneous velocity and average velocity is that average is over some defined elapsed time, maybe a second, maybe a minute, maybe a fraction of a second, whereas instantaneous velocity occurs over an infinitesimally small time frame. It is the limit of average velocity where the time elapsed approaches 0. This gives us the definition, the limit definition of the derivative. So this is the derivative. So this is displacement. Okay, and the derivative of displacement with respect to time. Okay, that's what dx over dt means. One way that we can also denote this that I want to introduce, although it will not be notation we use much, it will come up, and that is we can define a derivative with respect to time in physics as x dot. That tells us that this is the first time derivative in sort of shorthand notation of x. The first time derivative of x. The first time derivative of displacement. All right, so we have some practice problems. They're all fairly simple, okay? Type 1 are simple problems that involve motion diagrams and usually questions about average velocity. Type 2 are problems that involve x versus time graphs and or v versus time graphs and ask for information about secant or tangent lines. So they're graphical problems. The third type of problem are problems that describe motion of a particle or object and require an interpretation of the description and a solution of missing velocities or times, okay? Or displacements. There's some missing information you'll solve for. So these three types are really distinguished by the way they're presented. Diagram, graph, words, okay? Not all types of problems in the notes will be split up like this, but this was the natural splitting. And we only have one of each type of problem because they are fairly straightforward. Okay, so, well, not quite. We have two of one type, excuse me. Okay, so example 1. Here we have a graph. The position versus time graph below shows the position of an object moving in a straight line for 12 seconds. Notice that the vertical axis is a dependent variable of position, and the horizontal axis is time. We were first asked in part A, what is the position at 2 seconds, 6 seconds, and 10 seconds? This simply requires understanding of how to read a graph. So we would just look at the point 2, draw a line, see where that meets our curve, and it meets at 10. There's our answer. Likewise for 6, draw a vertical line, see where it meets our curve, that meets it at a position of 20, thus the answer is 20. Okay? And so on. Okay? Many of you have seen that before. Okay? Part B. What is the object's velocity during the first 4 seconds of motion? Okay? Okay, so we look here, the first 4 seconds, all right, that's from 0 to 4, so that's just this slope right here. So that would just be 20 meters over 4 seconds based on the definition of average velocity. Now here I'm saying that that is the average velocity. That also would be the instantaneous velocity at any point along this line because it's linear. And if velocity is linear, then average velocity equals instantaneous velocity because the tangent agrees with the secant. Okay? On to part C. What is the velocity during the time interval from 4 to 6? Well, that's this horizontal part, right? So 4 to 6 is right there. If it's a horizontal line, that means it's a velocity of 0, based on the fact that the displacement is x final minus x initial, and they cancel out, giving us a 0 in the numerator. For part D, what is the velocity during the time interval from 10 to 12? Well, now the displacement is negative 20, because displacements can be negative, unlike distances. Distances are always the absolute value of displacement, so they can only be positive. And here then, that means that we have an average velocity of negative 10 meters per second. It's very important to remember that velocity can be positive or negative. We'll talk about what that means in the next chapter. Hint, it means it's a vector, but we'll formally define that in the next chapter. What is the average velocity from 0 to 12? Well, in that case, the average velocity would be this secant connecting these points, because the secant is any line that connects 2 points. And we're connecting the point at t equals 12 to the point at t equals 0. So that means we would have a total displacement of 20 divided by the full 12 seconds, which gives us 5/3. I usually don't leave velocities as fractions, so we'll round it to 1.7. Why am I using 2 sig figs? I decided in this problem, since it's a pretty straightforward, very introductory problem, to just say, hey, let's just take it as 2 sig figs. Okay? Hopefully you'll allow that. Bonus question. What is the average speed from t equals 0 to t equals 12? So instead of asking for the average velocity, I'm asking for the average speed. Is it going to be 1.7 again? Is it? Definitely not. Instead, it will be the total distance, which is 20 plus another 20 plus another 20. So the total distance that the particle travels is 60. And it, of course, does that in 12 seconds. So the average speed is much faster. It's 5 meters per second. Okay? So good demonstration of how average speed and average velocity can be quite different from one another. Okay? Let's take a look at example 2. Example 2 is a type of problem that involves a motion diagram. Okay? A motion diagram is not like a graph, but instead is like snapshots in time. It's like taking photos and then overlaying those photos on top of each other. And that's what we're seeing here. We're told what happened at a particular point, and that both in space and time, and then what happened at another point in space and time. Okay? So taking the information in this graph, or in this diagram, please, and then let's answer the questions. All right, so in part A, we're asked what is the average, or the average speed and the average velocity. So first we'll calculate the average velocity. I'm reminding us that the definition is just delta x over delta t, displacement over elapsed time. So then it would just be 277 minus 19 over 4 minus 1. Why is that? Well, because this point here corresponds to a time of 4 and a displacement of 277. That's our final point, our x2, and our x1 is 19 and a time of 1. Well, it's interesting that our point 1 isn't at a time of 0. That's good to take note of. You've got to pay attention to the diagram. And then that gives us an average velocity of 86 meters per second. What about average speed? Well, average speed is total distance over elapsed time. And, well, that's the same darn thing, isn't it? Because it's just 258 over 3 seconds. So why do average speed and average velocity agree? Well, because nothing turns around. If an object, like this car, that we're treating as a particle, doesn't turn around, if it just continues in a straight path, then its average velocity and average speed will agree. Part B asks, is the car moving at constant velocity? And the answer is definitively no. Why do we know that? Because of a little bit more information that we can ascertain from this first second. If we notice, the average velocity for t equals 0 to t equals 1 is only 19 meters over 1 second, or 19 meters per second, right? Because it started at the origin at x equals 0 and only got to 19 meters in the first second. It wasn't going that fast because it had to accelerate. More on acceleration later. So if the average velocity changes, so must the instantaneous velocity, which is to say that velocity is definitely not constant. Do these examples seem very simple to you? Painfully simple? They probably do. Good. I want this early material to be as straightforward as possible. Well, let's look at example 3. Okay, just interpreting kind of a word problem about velocity. All right. So a particle travels back and forth along the x-axis in the following way. From t equals 0 to t equals 2 seconds, the particle moves at constant velocity in the positive direction and covers a distance of 25 meters. And then from 2 to 4, it continues to move in the positive direction and covers a distance of 50 meters. Okay, a greater distance in those next 2 seconds. What is the average speed? All right, it would just be 75, the total displacement, divided by the total elapsed time. And it turns out that the velocity would be the same. Why is that? Because like in the motion diagram problem above, nothing turns around. The direction remains positive for both segments of the motion of the particle. How far and what direction would the particle need to travel in the subsequent second after t equals 4 seconds in order for the average velocity to be 0 meters per second? So we're not being asked for a speed here, we're just asked for what must be that final displacement. Well, for the average velocity to be 0, then the displacement must be 0. That's the only way. That means that x final must equal x initial. So that tells us that the final displacement in the final second is just negative 75. We just have to go all the way back to where we started, and since we covered a total of 50 plus 25, we have to then go backwards 75, which is a negative 75. Because it's a one-dimensional problem, we define a particular direction as positive and the opposite direction as negative. That's it. Okay, so let's look at our last graphical one. This one, it will require the most thinking and probably is the deepest analysis of all the problems. Example 4. Draw an approximate graph of the velocity versus time graph that corresponds to the position versus time graph shown. Okay, so quick idea here. This is a derivative. I'm asking you to draw the derivative of this graph. Okay, to go from position to velocity is just a math problem. It's just going from a graph, a function, to a graph of the derivative of that function. So try it. Pause the video and try it. Then my solution will make more sense if you've already tried it yourself. Okay? I'm assuming you've done that. Now, let's take a look at it. Okay? I've drawn in green here little examples of tangent lines. Tangent lines, unlike secant lines, don't connect 2 points on a curve, but instead just touch the curve at a single point. I've heard them describing as kissing the curve at one single infinitesimal point. And that's what all these green lines are supposed to represent. They're not all the same steepness, but they represent the instantaneous slope, in other words, of the graph at that single point. Okay? Tangent lines. Representing instantaneous velocity, because the definition of velocity is the definition of a tangent line. Okay? So then I can piece together this information and I get the following. Instantaneous velocity must look like this, because I know here that the velocity is very steep and negative, and I know over here the velocity is very steep and positive, and I know right here the velocity is horizontal. Well, the tangent line is horizontal, thus the velocity is 0. Okay? Furthermore, since the steepness of these two tangent lines is vertical, the velocity is undefined, and those are vertical asymptotes. All right, so there you have it. Taking the derivative of this function gives us this one, graphically, okay? Because we weren't given the actual mathematical form. We weren't following the rules of derivatives of a polynomial, for example. We were just doing a graphical analysis of it. Okay, so that concludes the fourth and final example. I have 2 further examples for practice of 2 of the 3 types. I didn't give you a motion diagram problem because I don't really focus too much on motion diagrams. I just wanted to make sure to cover them. Side note, motion diagrams are covered in chapter 2.6 or section 2.6, which isn't really formally shown in any of the headings of the lectures for this chapter, again, because of the lack of focus that I give it. And not that it's a tricky idea, it's just one that, due to its simplicity, I'd rather just kind of leave on the side. But anyway, examples 5 and example 6, please complete them if you want some extra practice, such as those that go on the discussion boards. All right, well, thank you so much for watching this lecture video for Lecture 2, Sections 2.1 to 2.3.